So up till now, all of our u substitutions have involved indefinite integrals. And you can definitely do the indefinite integral version, find the indefinite integral, and then use that to evaluate for a definite integral. But it turns out we don't need to do that. When we're doing u substitutions on definite integrals, we don't have to back substitute to express something in terms of x when we plug in. Instead, what we do is we're going to change the bounds of integration from being values of x to becoming values of u itself. So this is going to look a little bit different, but it's really important that we remember that when we put the numbers here, they are numbers of this variable right here. The name of the variable is super, super important for consistency. So let me show you how it works on this particular example. The inside function here is 2x minus 1. So that has to be our u. So u is going to be 2x minus 1. Du will just be 2 dx. And so we can replace dx by du over 2. But we're going to do two more computations to change the boundaries. We're going to compute u of the lower bound, because this is a value of x, and we can view u as a function of x. When I plug in -1 into the x here, I get 2 times -1 minus 1. 2 times -1 is -2, minus 1 is -3. And similarly, we plug in 2 into this function, u of 2, and we get 2 times 2 is 4, minus 1 is 3. And so our whole integral becomes the integral from the lower bound of -3 to the upper bound of 3 of sine of u times, instead of dx, we have du over 2. Now, sine is an interesting function. Remember the sine wave? It's perfectly symmetric from the positive to the negative. So whenever we integrate from -a to a, the integral from -a of sine of x dx is always 0. That's because the area below is always equal to the area above. So because we're doing exactly the same length, from -3 to 3, this will always come out exactly to 0. And this is way, way, way faster than going through with a back substitution and everything else. You'll get 0 at the end, but it'll take you 10 minutes longer, I promise. So pay attention and do change the boundaries, because if I were to write -1 here and 2 here, this whole thing would be formally incorrect. You will lose points for putting the wrong boundaries for the variable here. Fair warning. All right, let's do one last example, and this should be it for the week. Let's try to do the definite integral from 0 to pi over 2 of sine x times cosine squared of x dx. Now, you'll notice that sine is a version of the derivative of cosine, and cosine is being squared. So cosine of x needs to be my u. And then du is going to be the derivative of cosine is negative sine of x dx. So now we're in business. We're just going to get a negative sign that comes up. But we also have to remember to evaluate our boundaries for the new variable u. So u of 0 is when I plug 0 in for cosine. The cosine of 0 is 1. And then u of pi over 2 is going to be the cosine of pi over 2. That is 0. So this is going to look weird, but this becomes the integral from 1 to 0 of cosine is u, so I have u squared. Dx is negative, sine dx is negative du. Now, I don't know about you, but I don't like having a bigger number here than there. It's not how it's supposed to be. But swapping them just flips the sign, right? This is one of the results we had in the definite integral section. And so we can just flip this over, go from 0 to 1, but then this goes from negative to positive. So this just becomes the integral from 0 to 1 of u squared du. And now we just evaluate u squared du integrated from 0 to 1. Well, that's just going to be u cubed over 3 from 0 to 1. I plug in 1 and subtract when I plug in 0. 1/3. And we are done. We don't have to go back to x's because we already changed the bounds. So this is how we do definite integrals with u substitution. It's interesting, but it's a slightly different step, and so you have to be careful to evaluate the new boundaries and plug those new numbers in for you. That is it for this week. Good luck.